So with statistical tests, we're not always 100% accurate. That's why we don't ever draw a 100% confidence interval. We sometimes make mistakes, and there are two different types of mistakes that we can make. The first one is called a type 1 error. This is when the null hypothesis is true, but we accidentally reject it. The second type of error is when the null hypothesis is false, but we fail to reject it and instead say we don't have enough evidence to reject that null hypothesis. The power of the test is often denoted as the Greek letter beta, and it is the probability that we correctly reject a false null hypothesis. Now here's a good visualization of type 1 and type 2 error. We have reality here. There's two different sets of reality. One is that the null hypothesis is true. The other alternative is that the alternative hypothesis is true. And then we have what statistics, our test, tells us. So here, our test is saying that we fail to reject the null hypothesis, and the alternative is that we reject the null hypothesis in favor of the alternative hypothesis. So one way of visualizing this type 1 and type 2 error is through a pregnancy test. If you're a criminal justice major, you could think about this test as a drug test, or if you're a nursing major, you could think of this test as a medical test for disease, stuff like that. That's what this is useful for. And so there's two different sets of reality. One reality is that the person is pregnant. The other reality is that she's not pregnant. Our pregnancy test, however, isn't 100% accurate. It finds HCG in her blood, then it reads a positive sign, and so it rejects that null hypothesis. But if it doesn't find that hormone of HCG, then most likely she's not pregnant, and it reads a negative sign. So it really just looks for this hormone called HCG and whether or not it's present in her urine. So there's four possible scenarios, two of which we could get right. So if we reject that null hypothesis in favor of the alternative, the test is going to read positive, and if she is in fact pregnant, then we get that right. If she's not pregnant and the test reads positive, that's what's called a type 1 error. So in this instance, we have stated that the alternative is true, but in fact, the null hypothesis is true. So we have mistakenly rejected that null hypothesis when it's in fact true. The other type error is the type 2 error, and this is when we fail to reject that null hypothesis. So in this instance, we've stated that she's not pregnant, the stick reads negative, but she is in fact pregnant. That's the other type of error that we could read. If the stick reads negative and she's in fact not pregnant, that's completely fine. So the likelihood of each of these different events depends upon the alpha level that we set, but it also depends upon the power of the test, and that's why this beta is written here, is we can determine what that power of the test is based on our sample size and based on the prevalence of the disease or of the pregnancy rate. So for most pregnancy tests, the accuracy that it reads on the side of the box is somewhere between 95 and 99% accurate. So it's 99% accurate when there is HCG in the blood, that it correctly identifies it. However, this isn't the likelihood that you want to know when you have a positive result. So if you have a positive result, what you actually want to know is the likelihood that you have HCG in your blood. The percentage that they give you on the side of the box is the opposite conditional probability. They give you the probability that it reads positive when in fact there is HCG in the blood. To find the correct probability, conditional probability, is going to depend upon how many people that you're testing and how rare pregnancy is or how rare the disease is that you're testing. So again, this type 1 and type 2 error is really important, particularly when we're dealing with tests like DNA testing for a criminal trial or drug testing where people could potentially lose their jobs. The rate of these errors, both the false positive and the false negative, they're really going to depend upon how many people that you're testing and how rare the DNA matches actually are, how rare the drug use prevalence actually is. So here's an example of a problem that tries to identify a type of error. So a basketball shooter has a poor foul shot percentage. It's 40%. He claims that he practiced a lot and he increased it to 50%. Now, we don't know what the true proportion actually is, so the coach, who's skeptical, asks him to take 10 shots, and the guy makes 9 out of 10. Is that enough evidence to say that he's actually increased his shooting proficiency? So if the shooter has not improved but still makes 9 out of 10, that's possible. It is probable to still get 9 out of 10 shots, even with this poor shooting percentage. But because he got 9 out of 10, the coach changes his mind and he thinks the guy's actually improved. But let's say in reality he hasn't. He hasn't improved. What type of error is the coach making? Well, the coach is making a type 1 error. What the coach has assumed is that the guy has not improved, and he runs a test to try to reject that null hypothesis. And because the guy made 9 out of 10 shots, he rejects that null hypothesis in favor of the alternative and says he has improved. So this 10 basketball shots is just his test of the proficiency. So it's just a sample of how good the guy actually is. In reality, if the guy's proficiency has not improved, then the reality is the null hypothesis is true. So if the null hypothesis is true and we mistakenly reject it, as the coach has done, that's a type 1 error. So again, these are the definitions of type 1 and type 2 error. They're going to be used in this exam and in the next exam because we're running a bunch of different hypothesis tests based on different parameters. So you may want to write these down for quicker references because you're going to see them again.